type them in now so that you don't forget them if you'd like. Type them into the chat window as we go along. And those plus any that you send me by email, I will answer and get back to you. So let's go ahead and get started. I think there are 7 repeated errors that I've seen in my 37 years. Some of them are errors because things have changed over that 37 years. And so the first thing I want to do is talk about the mistakes that people make when they deal with the thing called a p-value, what that means, and just go over that a bit. The next 3 errors have to do with what I call the flow chart. The basic idea here is that there are 3 errors related with deciding what test to use based on the shape of the data, whether it's a normal distribution or not a normal distribution. And I will give you a better flow chart and a better way of deciding what hypothesis test you should use. So those are 3 errors related to hypothesis tests. Error number 5, we'll talk about the most common one with regression, and that there are good things, better things than R-squared for evaluating regression equations. Talk a little bit about outlier tests and why they're not often very helpful. And then finally, just the most common error in data when you have detection limits. So those are the 7 errors that I've decided to emphasize because they seem to be the ones that are most commonly used. All right, error number 1, that a significant p-value tells you all you need to know about a test or a regression equation. And that's not really right. There's many other things that you should look at, but I'll focus on a few. And that comes from the fact that people often don't understand what a p-value is telling them. So it gives you some, p-value gives you some measure of the evidence against the situation where there's no signal. And that's significance is not the same statistically as usefulness, as something that would be practically useful to you. So what is a p-value? P-value is the probability of seeing a signal, like difference in means between groups, or a correlation, or a trend. All of those are signals when there is no signal in the real world. So it's the probability of a false positive, of seeing something or apparently seeing something that's not there out in the field. And a low p-value doesn't prove that there's a signal out in the field. It only says that it's likely. So the p-value gives you a measure of how unlikely the no signal, the null hypothesis is. So its primary use is to help people decide what to do. That's the hardest thing for a human being to do, and that's to make a decision. So which way do the data indicate that there's a signal in my data or that there's not? That's what a p-value can give you an indication of. So here's one example. Here's total dissolved solids, or TDS. This is a rather old data set, as a function of stream flow, which is capital Q, in a regression equation. And you can see underneath where it says estimate that there is a slope coefficient, and then across in a very typical regression table, the p-value for that coefficient. This p-value is 10 to the minus 10th, so there's going to be 9 or 10 zeros out before you hit the 1. So it's a very small number. It's telling you it's very unlikely that this would occur just by chance when the null hypothesis is true. Very unlikely that you would see and estimate a slope coefficient of this magnitude for this data when there is no signal. So it gives you an indication that there's a signal. Does that tell you that this is a great regression model? No. Here's a picture of the regression, and the regression does not fit the data very well. Why? Because the data are curved. The regression line's a straight line model. So a very simple example, but just going through and looking at a table of an output and a p-value isn't everything that you need to know. And in almost every situation, certainly every one I can think of, There's no substitute for doing a plot and seeing what the model looks like, or seeing what the difference in the groups looks like before you make a decision. So do not base it based on just a single number. Here's a second example. This was differences between pairs paired by dates of lead concentrations, if I remember it correctly. And so this is a box plot of the differences and a test for whether the median difference equals 0. So the median is the line in the middle of the box, of course, and it's a value of 1 here. And so the test will be testing whether this value of 1 can be distinguished from 0. And the p-value is a value of 0.017. That tells you that if it was truly 0 and there was no difference out in the field between lead concentrations in 2001 and lead concentrations in 1996 at a variety of different sites, if there were no difference, you'd see a signal like this as consistently above 0, as this, about 1.7% of the time. That's what the p-value of 0.017 means. So it's not a very common result that you would see if it was really a 0 difference out in the field. So most people would say that's a fairly small number. I'm going to reject that there's a 0 difference out in the field. That's my assumption. And based on the data that I've collected, I'll declare that there is. When you do that, don't just compute the p-value, report a confidence limit. So in this case, a 95% confidence limit on that median is 0.1 to 2 micrograms per liter. It's important information. Why? Because this may be statistically significant. It may show you that there has been an increase in lead in this 5-year period, but an increase of 1 microgram per liter may not be useful at all. It may not be something that matters to you health-wise, environmentally. So whether or not there is a statistical significance doesn't tell you whether there's something that's useful, whether there's something that you care about, whether there's something of concern. So statistical significance is not the same as usefulness. So just to summarize here, number 1, the significant p-value does not tell you all you need to know. First, understand what a p-value is. It's the probability of a false positive, a false statement of difference or trend or correlation when there really is not one out in the field. And that small p-value doesn't mean you have the best equation if this is a regression that you could come up with, so you need to do some work, even if the p-value is small, and see whether the model fits the data very well. And a small p-value doesn't tell you that the magnitude of difference is anything that you might care about or would be useful, or you would decide to do anything about it. So statistical significance is not the same as usefulness. All right, second and third and fourth, the next 3 errors have to do with the flow chart. So this is probably a flow chart that looks a lot like flow charts you've seen in a variety of guidance documents. I've seen them in state documents, federal documents, company documents. And so it starts at the top where these orange letters are and says, let's assume that the data to start off with look like a normal distribution. And then we'll run a test to decide what type of test that we want to run. And this is for the situation of comparing groups. So first I'll run a test for normality. So it's an assumption that the data follow a normal distribution. If you cannot prove that they are non-normal, so you have to go with the assumption of normality, you'd go over to the right and run a t-test or analysis of variance, depending on how many groups there are. These are the traditional parametric procedures developed back in the 40s and 50s. If that test for normality shows that the data do not look like a normal distribution, and most things in the natural world, certainly in soils and water and air, in organisms, very rarely look like a normal distribution. So if you can detect that difference from a normal, if the shape does not look symmetric, then you would reject the null hypothesis and come down to the second line here, according to this flow chart. I'm not a fan of this flow chart, by the way. I'll tell you a better one. And so even then, we're going to try to hang on to using ANOVA or t-tests and say, well, maybe I could take logs, take the logarithms. If now the logarithms do not look anything different than a normal distribution, at least as far as I can tell, and telling that is a function of the number of data you have. If I cannot tell that they're non-normal, I'll run over here and do the analysis of variance or t-tests on the logarithms. And when you take logs, you've just shifted in what the objective is and what the test is actually doing. And then finally, if the test on logarithms does not look like a normal distribution, so we would reject the null hypothesis of that normality test on the logs, then a non-parametric test is allowed to be used. And when you use a non-parametric test, you are then computing another different objective. And so the problem that I have with this, there's several, but the primary one, the one I want to focus on today, is that these tests have different objectives. They test different things. And really what we should be using is a flowchart that says, this is my objective, therefore this is the test I'm going to use. So let's start off with error number 2. Testing for a normal distribution first to decide whether to employ a parametric or a non-parametric test is not a very good practice. Why? Because there are tests that will meet various objectives, and you should decide based on those. Most people use this test for normality because they're thinking about running a test. I'll call them parametric tests here, that's the general name, that assume the data, they require the data to have a specific shape. And there's really no need these days to run a test like that. There are very good tests that do not assume a normal distribution. So decide which type of test to run based on your objectives. And the primary difference in objective is, am I interested in the mean or am I interested in a typical value? When would I use a mean? I'd use a mean when I'm interested in totals, when I'm interested in things that accumulate. I'm interested in mass, volume, total exposure. When would I use a median? When I'm looking for typical patterns, differences between groups in general. Does one group generally give me higher values than the other? Is there a trend? Do concentrations generally increase or decrease over time? Those latter questions are frequency questions, and there are tests that test frequency questions. So tests on means and tests on medians answer two totally different questions. And it doesn't make sense to decide what question you're going to answer based on the shape of the data that you observe. Use a test that answers the question that you're interested in. So here's an example. Two sets of data. One is down gradient and one is up gradient. They're down gradient and up gradient of some remediation. And we've got concentrations. They happen to be molybdenum concentrations. And so we'd like to know, perhaps, is one group higher than the other? And you might suspect that the up gradient is higher than the down gradient before you ever looked at this, because the whole purpose of this was to try to decrease those concentrations with some kind of remediation. So let's run a test. We test to see if these groups look like a normal distribution or not, and then test for difference in means if they don't appear different. One of the groups actually tests out to be different than a normal, and that's the one at the bottom down here. There's 13 observations there. The one that's the up gradient group does not test to look like it's different than a normal distribution. There's a fairly small amount of data there. And so we cannot decide based on that what to do. So let's do what most people do, and that's hope. Let's hope it doesn't matter. So we run a t-test, and the t-test gives back a p-value between a mean of 4 for the up gradient group and a mean of 1/4, 0.25 for the down gradient group. That p-value is 0.14. Most people's cutoff for these p-values is the traditional one of 0.05. So this would say there's 14% probability that you could see this difference if you look at it through the t-test's point of view, which is not the same as what's being plotted here. But if you looked at it that way, there's about a 14% chance that you would see this when there is no difference. That's not strong enough evidence for me, the t-test, to decide that they're different. You should note that the t-test requires normality for each of these groups, and it requires equal variance, which we're radically violating here for these two groups. And if either of those is not true, that will push p-values higher. Okay, so that would be the appropriate test, perhaps, if we were in a normal theory world, which we do not have to be today. Second thing would be, if I'm interested, is one group giving me higher concentrations than the other? Forget the mean, let's just talk about a pattern. Does one group look like it's higher than the other? That's what a non-parametric test tests for. It tests for differences in the CDFs, the cumulative distribution function, the set of percentiles between two groups. It's usually stated as a test for difference in medians, because most people are focused on the center. So is it typically the case that the concentrations in the up gradient group are higher than the down gradient group? Could I say that I generally decrease concentrations by this remediation? All of those things are a way to say what the non-parametric test tests for. And the two-group test is called the Wilcoxon rank sum test. Its p-value is quite different, 0.01. It sees the difference between the two medians, and that's because it's not affected by any non-normality or unequal variance. So, decide which test to use based on your objectives. If you were interested in the totals, were the total amounts in one group different than the other, then you'd be interested in a mean. I still would not use a t-test. But if you are interested in the pattern, use a non-parametric test. So this is my flow chart. What's your objective? If you're interested in mass, totals, chronic, long-term effects, accumulating effects, use a test on means. And as I'm going to talk about, you'd use a permutation test. Those are tests that have come along since the 1950s that will test means without assuming a normal distribution. Or if you're interested in typical patterns, does one group give me higher numbers than the other? Or concentrations generally increasing? Then test for differences in frequencies or percentiles, and that's what non-parametric tests do. A rank is really just a transformation of a percentage. Okay, so second concern, let me step it up a little bit, and the power of tests is the big issue with parametric tests. That older parametric tests have low power whenever data have outliers, or they're skewed, or the groups have different variants, and so the low power means p-values get pushed higher. And that's the situation we deal with all the time in the environmental sciences. Usually, I deal with data that have all three of those characteristics. So ANOVA, analysis of variance, testing for multiple group differences in means, t-tests, testing for two group differences in means, or just even a confidence interval using the t-coefficient around a mean, don't work well for the type of data that we encounter usually. They have assumptions built in that we don't meet. So what's the alternative? Permutation tests are tests on means that do not assume that normal distribution. They're not bothered by outliers. They do have some effect on them by unequal variance, but that effect is really the effect on the null hypothesis in the way that you state it. So it's about as good as you can do with tests for means. Non-parametric tests don't assume a normal distribution, not bothered by outliers or changing variance, and they test for differences in typical patterns or percentiles. And this is just a quick chart of power, typical power. If data were exactly normal, and the only way that that would happen is if you generated the data, then there's about a 4% a 4% benefit of using a parametric test like a t-test. That's a fairly small difference. If they're approximately normal, by that I mean they would not be rejected as a normal on a probability plot with its associated test. You'd see data bouncing around a straight line, but a nice straight line pattern. You'd see box plots that look equal. Then the data are approximately normal, and they'd have equal power. Whether it was a parametric or non-parametric test, there would be no disadvantage of using one versus the other, except that they test for different things. And then, if the data looked non-normal, the typical skewness and unequal variance, non-parametric tests have a huge power advantage over parametric tests. And the permutation tests would have a similar power advantage over the older parametric tests. So, choose the type of test based on your objective, not on the shape of the data. If concentrations are to be tested that they're higher in one group than the other, that's a question of frequency. Do I see in one group a higher frequency of high values than the other? Then use a non-parametric test. That's exactly what it tests for. Are concentrations increasing over time? That's a frequency question. Are higher concentrations more frequently occurring now than they did 20 years ago? So that's a frequency question. Use a non-parametric test to test for it. If you have total amounts you're interested, how much has been washed, carried down into the estuary over the year, question of mass, and you want to deal with means. And if you're doing testing in that situation, test for means without assuming normality using permutation tests. So, just to summarize for the second error, field data rarely ever follow a normal distribution. If you have skewed data with outliers, non-parametric methods have a large power advantage, and they answer the questions that at least most people ask, in my experience, questions about frequency. But if you are interested in means, then use a permutation test. And don't decide on what type of test to use based on the shape of your observed data. Decide what question you want to answer, and then go ahead and use the test that answers that question. Okay, I did mention that for questions, you can type them in the chat window, but if you just send them to me by email afterwards, I will distribute them to everyone. So, we will go ahead and do that, and I will ask for those explicitly afterwards. All right, then finally, for the flowchart set of errors, using t-tests and ANOVA with small data sets don't have much power. So back to a question of power. This is in the top decision here. If you cannot see that the data are non-normal, and you send it over to an ANOVA or a t-test, and if you really don't have data that follow a normal distribution, you'll have low power. So people have talked a lot about power and t-tests. Power and the number of observations you need in order to just assume the parametric test, the t-test and ANOVA work well, changes with skewness. And for the type of skewness that we deal with, if you need a rule of thumb, that rule of thumb is a lot closer to 70 than 30. So 30 really has nothing to do with this question, even though it's one of those urban legends I've talked about in other webinars. So with 70 observations, perhaps you can go ahead and use a t-test or an ANOVA. That's 70 observations per group, but a permutation test would let you do that without assuming normality. So there are better tests always than doing this. So here's a set of data. There's 9 observations. I cannot reject that there's a normal distribution with the test because the p-value is greater than 0.05 with the Shapiro-Wilk test, the standard test for normality. These data were generated. They were generated from a log normal data sets, so they don't have a normal distribution. So you could be in the situation, especially if you don't have large data sets, where with the traditional flow chart, you'd be running tests that would have low power and have a difficult time of seeing differences between groups. So testing and interpreting the mean when data are skewed has been one of the most difficult issues in statistics for decades. In the past, people, and these are more environmental science people, assumed it didn't matter and ran the parametric test anyway. And this problem, which that can get you into trouble with having low power and having p-values that are too high and not seeing differences that are there, was solved back in the 1990s and 2000s with the development of permutation tests. And that's actually not accurate in the sense that these permutation tests were envisioned back in the 1930s. They just didn't have the computing power to do them. So in the 80s, a lot of the theoretical work was worked through for permutation tests. In the 90s and 2000s, the software became available to do them. So these are tests that will test for differences in means without assuming a normal distribution. That's their huge advantage. So what they do is they use the observed data and all possible rearrangements or permutations of that data in order to run the test. So this is an example. Let's think about the null hypothesis. This is just two groups of data. The clear data here are in the above group. The blue data are in the below group. And we'd like to know whether the means of these two groups are the same or not. If the null hypothesis is true, this group assignment is arbitrary because we're saying that under the null hypothesis, when the null hypothesis is true, there is no difference in the concentrations. So the fact that I observed a concentration of 6 in the above group doesn't really matter. It could have just as well have been in the below group, because there is no difference in the concentrations between the two groups. So when the null hypothesis is true, this group assignment doesn't help me to distinguish concentrations. They might as well have been in the other group. So I could, and the computer will, randomly reassign the group assignments. And we'll call that a shuffle, just to kind of relate it to iTunes here. So in this shuffle, the 6, which was originally collected above in the above group, it gets assigned to the below group. And the 10 gets assigned to the below group, and so on. So we rearrange the locations, then compute a mean of the 3 above group data as they are reassigned. So that would be a mean of the value of 5, and the mean of the value of 16, and the mean of the value of 22. Those 3 values together compute their mean. That would be the mean of the above group. And then the data that are now assigned to the below group would be 6, 10, 8, and 18. We'd compute that mean. And that would be one random permutation, one shuffle, that, if the null hypothesis were true, is equally likely to the one that we observed. So what permutation tests do is rearrange those data assignments to groups and compute a test statistic. This test statistic is just the difference in the two means. And when you rearrange them, you get a picture, and if you do that many thousands of times, you would get a picture of what the null hypothesis looks like. And that picture is one that's a picture without assuming that the data have any particular shape. Parametric tests required the assumption of a normal distribution because they could not do this. So they used the assumption that the data had a normal distribution to say, here's what the shape of the outcomes looks like. If the data were normal, then this outcome might have been a t distribution or an f distribution or something else. We can just look at all the possible results. In this case, with this small data set of 3 and 4 observations, there's 35 results. This is the observed value that we got 2 slides ago, the value of 9. The p-value is the probability of getting a 9 or something more extreme when the null hypothesis is true. And so the proportion of the area that's in red here of the total is our p-value. And that was computed without assuming a normal distribution. So in this two-group case, the p-value for the permutation test is 0.0018. There's no more data being used than with the t-test. That's a pretty big difference in p-values. The difference is simply a measure of the fog of the t-test because it was assuming equal variance and a normal distribution. And we violated both of those assumptions with the data. So here we would say that the means are very likely to be different in these two groups. And they are, I think, just from the graph, likely to be different out in the field. We are likely to have decreased the mean concentration of molybdenum, not just the typical change from the medians. So permutation tests, there really are no disadvantages of using them over the t-tests and ANOVA. It's just that we're not familiar with them in environmental sciences. So this summarized as those just saying, use a permutation test if you're really interested in differences in means. Do not use the older normal theory tests. Back in 1935, Pearson, I believe it was, said these normal theory tests, assuming a normal distribution, running a t-test or an ANOVA, these are approximations. We know what we want to do, we can't do it. We don't have the computing power yet. You people 50 years later will be able to do them. He said something like that anyway. So now we can do them. All right, moving down to the last error with the flowchart, and then I'll skip through the rest pretty fast. These are really the ones I think are the most important right now because it's the ones that I see most commonly. So jumping down, take logs, run an ANOVA or a t-test on the logs if the data looks skewed to begin with. What are we doing when we take logs? We're putting the data on a different scale. So maybe I should try in this case to take logs and run a t-test. That would be the thinking here in the old way of doing things. So here's a plot of the logs of the data. They look fairly close to a normal, fairly close and equal variance. Oftentimes that does occur. We test for the mean of the logarithms. That's these red dots in log units, whether they are the same or different. What does that mean back in the original units? It means you're no longer testing for the means in the original units. If you transform those means of the logs back into original units, you're testing for geometric means, which are the blue dots right here. And those geometric means are actually one way to estimate a median of the groups. They are not estimates, or at least not good estimates, of the mean of the groups. So by taking logs, you've changed the objective. It's a great way to test for typical values because that's what a median is. But it is not a test for means. So if you were really interested in a test for means, by taking logs, you no longer have it. So if you're really interested in means, use a permutation test rather than taking logarithms. This would be a great test for medians. The p-values often turn out to be very similar to the non-parametric tests because those test for differences in medians. So, bottom line, use the test that answers the objectives that you want. You'll have to think through, what are my objectives? And use a permutation test if you're interested in means. Use a non-parametric test if you're interested in frequencies, typical patterns. All right, those are the first 4 errors. Moving on for the rest of the time, error number 5 with regression, that people tend to use just R² to find the best regression equation. And you need to realize that R²'s in units of the Y variable. I know that it's a unit-less mathematically number, but it's in the direction of the Y variable. It's an expression of the proportion of the variance in the Y variable that's being explained by a model. And so what happens if you change the units of the Y variable? If you change the units of the Y variable, you've just changed the units, at least what the meaning of 1.0 is for R². You've changed the maximum variation that the R-squared is being computed against. So you're changing things to the point where you really cannot directly compare R-squared in the original units and transformed units, say if you took logs. And in fact, with logarithms, you can actually explain more of the variation in the original units, often when data are skewed and have some outliers, by taking logs and having a lower R-squared in log units. And I can't give you a rule of thumb by how much lower, but some lower. If you had an R-squared of 0.65, it's very likely it's a better explanation of the variance back in the original units than a regression in the original units with an R-squared of 0.7. So directly comparing them is not possible. Also, R-squared depends on the slope. And there are better numeric criteria than R-squared for determining what's best. So just a simple plot. This type of plot goes back teaching this kind of stuff 30 years ago and more. That if you have a lower slope line and an upper slope line with the same variance, I just mathematically increased the slope of the data, same variation around the line in terms of magnitude. They have very different R-squareds. And the problem is that we had no control over the slope in the natural world. We can't go out and design experiments to maximize slopes. So we have to take what we get. So R-squared has various things that affects it other than what we're trying to evaluate, which is some measure of the goodness of a regression equation. And this is just a picture of 85% R-squared, 0.85 in log units, and an R-squared of 0.87 in the original units. That's pretty close, but it would turn out to be a better explanation of the variation because this variation actually is increasing a bit as you go higher. And that's something that a log set of units models well. So the better methods, one is called AIC. Most of these better methods are cost-benefit analyses. The costs are usually the number of X variables that you put into the model. P here is the number of parameters, the number of X variables plus 1 for the intercept. And then some measure of error. There should be a plus sign in the middle there. So you can add that in on your paper copy if you have it. And by the way, the PDF file of all these slides was put up on the Practical Stats site in our download page. You can go and download it if you didn't get that email that's told you that. So it'll be there for the next week or so. So there should be a plus sign here, and I believe there is in the PDF. Some things don't carry over well into the webinar software here. So this is a measure of error and unexplained noise. That should decrease as we add more variables. And if those variables are really important, if those X variables are explaining a lot of the error, this goes down more than the 2 times the additional variable goes up. So there's a trade-off. And these measures of quality look at that trade-off and say, is it worth adding in a new variable for, is it worth that in terms of the amount of error that I can explain, the amount of error I can pull out of the denominator of my test and stick in the numerator as part of the signal. So better methods, better regression equations would have lower AICs. And you can compare those directly. So just an example where the R-squared is highest with 6 variables in the model because R-squared always goes up. AIC says to select a 5-variable model, so it doesn't pick the highest one. The last one, variable, whatever that is, doesn't explain enough to really make a difference. And you could see that with the small change in R-squared. Another measure called PRESS, which is a measure of predictive ability. It's one of the best measures to use if you're trying to predict new values somewhere in the future or at different locations or different times. That would have picked a 4-variable model. Mallow-CP is something very much like AIC, a cost-benefit kind of procedure, also would pick the 5-variable model. So these are better tools, depending on your purpose, better tools for deciding what is a good regression equation. There are others, BIC and a number of others. So much better than just plain R-squared. So I would get into the habit of using them. All of your standard regression software these days, at least in statistics software, will print those out. I don't believe Excel has AIC and Press and those things. So, summary, using R-squared to find the best regression equation is not the best procedure, and there are better methods. And just pick up a book on regression that's been written in the last 15 years, and it will have some description of those other better criteria. And those criteria are available in all the standard software packages, all the statistics software packages. Error number 6, outliers. The bottom line for this is that there is no test in statistics for what is good data. That's a science question, not a numerical question. So there are outlier tests. What do? They don't find the bad data. They find different data. And you have to use your knowledge of science to decide if they're bad or merely different. So those tests, the Dixon and Rossner tests, are two of the very common tests for outliers. Dixon focuses on whether there's one outlier. Rossner's lets you test for multiple outliers. You do have to tell it ahead of time. These are the number of outliers that I have, I think. These tests, what do? They say, how likely are my data to have originated from a normal distribution? That's all they are. And the problem is that's not what people are using it for. They're using it for tests of badness. And as I've already stated, it's very unlikely that data that you collect in water, air, soils have a normal distribution. So you most often will find in every data set you deal with one or more outliers because the data don't follow a normal distribution. And the question is whether that's bad or not. And these tests don't answer that question. What do cause outliers? An error in measurement. So if you could find that, you can plot the data, you can run these outlier tests, see that they're outliers, and then say, I better check that number. So if you find that there's an error, fix it or drop it if you can't fix it. But there's other sources as well. Contamination is the semi-statistical term where you have another population, another different set of data that have different characteristics, and they're blended together. So you have some background data, and then you have 1 or 2 or 3 values that actually have received contamination. Maybe they're over on one corner of the site. And so when you put all those together, the others look like they are outliers. If you want to describe the site and its characteristics, maybe compute a mean and think about the total mass that's in that site in the soils or in the water, then those data should be included. If you're trying to define background, then those should not be included. So that's this decision is one that's made by you as a scientist, not by a statistical test. And then there are many distributions of data in the natural world that are skewed. Many processes of adsorption, diffusion, and other things lead to skewed data. Just the fact that you have a zero lower bound. If you measure things that go down close to zero, they're going to be skewed, which means that some of the higher values will test out as being outliers. Does not mean there's anything wrong. It's just that you have skewed data. So just as an example, I generated a fairly mild skewness, much less than I usually deal with in data from the field. Has one outlier. Other than that, it looks fairly close to a normal distribution. And so the outlier test says, yep, that's an outlier. But these were actually generated from a log normal with a fairly low skew. So I could take logs. Here's the data. And now the point is does not test out as an outlier. It turns out on the box plot to be the upper end of the whisker because it's the highest value, but it's not an outlier by the Dixon test. So can you say that you have a data set with a data value on the previous graph that is an outlier and it's bad, and now you take logs and it's no longer bad? No. So badness or goodness you're going to have to define by science. Outliers, deal with them. If you're not worried about using tests that have require a normal distribution, then don't worry about them for the most part, except in terms of concept, that You have to think through why they're there. But they won't mess up a permutation test. They won't mess up a non-parametric test. So usually they have been deleted in the past because people were using t-tests and ANOVA. And t-tests and ANOVA are, some younger people would say, so 1950s. So not something that we need to use today. So you can use tests that don't really care about the outliers. You may care about them just to decide if data values are wrong, or that there is some non-background data mixed in and I'm trying to look at background. But those science questions are things that you could use as a follow-up from either these tests or even just a simple plot, but they don't define bad. That's the summary for this error. They're often the most valuable observations in the data set. They tell you that different conditions were used or some unusual event, one that maybe you're not able to go out and sample a high flow event or something like that, and so they may tell you something that's the most valuable thing in the data set. Albert Einstein was an outlier, so don't be too quick to leave. And then finally, substitution. Substituting 1/2 the detection limit for non-detects. Has been the most common in the past method for dealing with non-detects, either 1/2 or the detection limit itself, or 1 over the square root of 2 times the non-detect. Any of those values, whether it's 1, 1/2, 2/3, 0.01573998, whatever value you want to multiply times the detection limit, has problems. Why? Because you're putting in a signal that's not there in the data, and that signal is not neutral. It produces invasive data that's alien to your natural ecosystem of data. And what it's putting in is a pattern of what the detection limits were in the laboratory or laboratories. And those often change. They change for structural reasons. Most of those reasons, they're not good when you plug that same pattern into your data set, because what you'll often find is differences in groups or changes over time that reflect the change in the lab, not anything to do with what's in the field. And there are better alternate methods. So just a simple example, here's some data that have a nice straight line pattern, some noise around the straight line. A correlation would have a correlation Pearson's R coefficient of 0.81. Regression would have a significant X, a significant distance variable here. That would be significant. Its slope would be significant. Nice idealized pattern. What happens if some of these are non-detects? And so I here have two detection limits, one at 1.5. There would have been a detection limit of 3 and a detection limit of 1.5. And I've put in 1/2 the detection for each of these. It doesn't matter which number you put it in, because if you're using that constant value, then what you're putting in is a flat line. And that flat line is a very different signal than the regression slope. And so what you're doing is, by default, you're lowering the correlation, you're lowering the significance of any regression coefficients. You've not put in something that ignores the data. You've not put in just, oh, it's halfway between the possible values of 0 and the detection limit. You've put in a flat line. So when you start to think beyond just one number, but multiple numbers, and use substitution, when you do substitution multiple times, you're putting in a pattern, and that pattern's not the one that was in the field. And this is just the classic example of a trend analysis, where there's a bunch of data that's bouncing around, but there is no trend in the aquifer or the stream. Detection limits go down over time, so you can put in the detection limit value, or 1/2 or 2/3 or whatever, and your values will start to go down over time. By substituting, you're putting in a downtrend that was not there in the data, and you'll get a great significant trend test that's not there. So you don't want to do that. We've known these kind of things for a long time. Here are two esteemed statisticians who are gray, at this point, and published something back in 1986 that said when you're thinking about means and medians and those kinds of things, summary statistics, substitution doesn't work well. There's better methods. They listed some of those methods. So that is now 30 years ago. Am I counting that right? 30 years ago this year. Okay. A little bit more recent, 10 years ago, the developers of the ProUCL software package at EPA said, if you're trying to compute a UCL 95, a confidence interval around the mean, if you substitute 1/2 the detection limit, and I'm sure this applies to the other substitutions as well, you can get a very poor estimate of that T interval with substitution for as low as 10% of your observations. So they said, do not substitute in 1/2 the detection limit. And they provide in ProUCL better methods. One's called the Kaplan-Meier estimator. You should be using those methods, not a T interval after substitution when you're computing intervals. For regression, a paper back at ES&T in 2003 found what we just saw with that picture, that when you substitute, you get bad estimates. You actually get slopes that are too low, just like we saw, because you're blending in zero slope data. And you get slopes that are artificially significant, because in addition to putting in flat lines, you're also putting data in that don't vary. So the overall standard error, the standard deviations are too small. So you should stop doing it. There are better methods that can fall into 3 different classes. I can't go over them today, but you can find them in the textbook that I wrote, the most recent versions, 2012. You can just classify things as they are above and below a single limit and look at changes in percents above versus below. Those are binary methods, including, say, logistic regression, which is very helpful for saying, is the percent of my detected values where detected is detected above 5, a unique number. Does that change over time? That sort of thing. You can rank data and run non-parametric tests. There are survival analysis methods, things that were developed usually in the medical statistics, that handle multiple thresholds, multiple detection limits for us. And those are all in that book, so there's the reference. So don't substitute. It does cause problems. It can put in a signal that's not there, like the trend example. It can not see things that are there, like the regression example. So